Okay, I'll have your exams on Monday. It's been, can you pass that back to Sam? Yeah. I'll have your exams on Monday. I may post the exam key today, but I'll have them all ready on Monday. It's just been a bad week. So, in terms of aldehydes and ketones, we'll kind of finish that up today. When we talked about reactions of the aldehydes and ketones, what we've done is we've added water, we've added alcohols, so we've made hydrates, we've made hemiacetals and ketals, full-blown acetals and ketals. We've looked at how that reacts with how sugars form those compounds, and then how we can use those as protecting groups. So what we're now up against is, let's add a nitrogen group to the carbonyl. And the mechanisms are going to be slightly different. So the first thing is nitrogen. If we look at the periodic table, our CNOF shorthand periodic table, nitrogen is stronger or weaker as a base than oxygen. Stronger? So if nitrogen's stronger as a base, what is it as a nucleophile then? Stronger or weaker? I mean, my ultimate question here is, what's stronger as a nucleophile, nitrogen or oxygen? How many people say nitrogen? Oxygen? Don't know. It's a horizontal relationship, which means with a horizontal relationship, the basicity is directly related to nucleophilicity. So the stronger base is a stronger nucleophile, which means stronger nucleophile is nitrogen. So that means I don't need acid. So I don't need to protonate the carbonyl. As a matter of fact, if I did add acid to this, what would happen? The nitrogen would become protonated. It's no longer electron rich, it's electron poor. And so it's not going to react. So we do not need acid for these reactions. Nitrogen is going to directly react with the carbonyl. Okay. And let me go through the mechanism and the types of molecules that you can get here. So there's actually two different names, which I'll kind of clarify. So the first thing is, this is first reaction is of a primary amine. So what is a primary amine? One with one carbon group attached to it. So if you've got one, it's primary, two, it's secondary, tertiary. Amines have no hydrogens on them. So there's going to be two different mechanisms for a primary and a secondary amine. So the primary amine then comes in, adds to the carbon, pair of electrons moves up to the oxygen. So again, these are all equilibrium reactions, so I get an O-, and I'd have the same mechanism if it was an aldehyde. And so now I end up with the positive charge on the nitrogen and a negative charge on the oxygen. So whenever you have a species with a positive and a negative charge, I guess the older term for that was calling it a zwitterion. And so that's what we have here. Now, what's going to happen is the hydrogen on the nitrogen is going to transfer to the O-. So we can, it's perfectly legitimate for us to just draw the arrow like that and have the OH pick up the hydrogen from the nitrogen. Now, we should realize that that's probably not going to happen that way. Most likely, the O- of one molecule is going to take the NH plus from another molecule. It's not going to wrap around. There's not enough space for that. But that's what's going to happen is the molecule is going to go back to being neutral. Remember, there's no acid in this case. So then what happens is that this whole process is done usually with heat. And so this is an example of addition, which I've just done, and elimination. So now I'm going to eliminate water. And the way I'm going to do that is this pair of electrons is going to move there. The OH is going to leave so that I'm going to lose H2O. And I'm going to form a double bond to the nitrogen. And so basically that looks really, really unsatisfying because you're just losing water, and you're probably doing that because of heat. Or it could be one of these reactions where the OH is pulling, where the OH of one molecule is pulling off the NH of the other. But as ugly as that looks, that's the way we're going to write it. Because you could say, well, why not just protonate the OH and have water leave? No acid. There's no acid present. So now I'm eliminating and I'm forming this molecule. If this R group is an R group, this is what's called a Schiff base. And if I started by taking NH3 and adding it to the aldehyde or ketone, then if the R is not an R but an H, this is what's called an imine. So technically an imine comes from ammonia, and the Schiff base comes from everything else, although we'll use those terms interchangeably. So this is the addition-elimination reaction. It is an equilibrium reaction. So that if I was to write, for instance, down here, that equilibrium would be amine with an A, reacting with ketone, making imine with an I, plus H2O. The way to shift this equilibrium to the right is one of two ways. Either remove the water as it's formed, or, as I'll show you on the next slide, the imine or the Schiff base will actually precipitate out of solution. And so if it precipitates out of solution, that pushes the equilibrium all the way to the right. Okay. So that's the formation of a Schiff base, or the formation of an imine using ammonia. Okay. And there's nothing exciting there. It's steps that we've kind of done in the past. Now let's go back to this slide. So why? Well, first of all, I'll show you historically how these were used. We don't necessarily use them that way, but it does kind of tie into what we're doing or have done in lab. So if you react the primary amine, you don't make an imine, you make a Schiff base. And the only way it's an imine is if it's NH3, and that forms that's the imine. With the NH as opposed to the NR. Now, some of you that were in lab yesterday heard my tale about my Organic 2 lab experience. where we were basically, for the second half of the lab, we were given 4 test tubes of unknown materials, and we had to figure out what they were. We had we had a really small NMR. You also heard my tale about that. Didn't necessarily work all that great, or at all, or we weren't allowed to use it. So we had to figure out what our unknown compound was by doing what are called qualitative tests. And we know some of these, actually. We've done some of these, or we've learned about them on paper. So, for instance, if you thought you had an alcohol, you would take a small piece of sodium metal, drop it in, and if it fizzed, it was an alcohol. If it was a carboxylic acid, you might add a little bit of sodium bicarbonate to it. If it fizzed, then it was a carboxylic acid. If you thought you had a double bond, add a drop of bromine. If the orange color disappeared immediately, it was a double or triple bond. So, and then you could use the, if you needed to know if it was internal or terminal, you could do things like ozonolysis. So we do all these different chemical tests to determine what the functional group of the molecule was. And this is how people had to do those, had to identify molecules before spectroscopy. So once we had an IR, it wasn't bad. At least the one wasn't bad. We could get an IR and then we could tell what functional group we had. We'd have to do all the tests. So if you thought you had an aldehyde or a ketone, or the way to test for an aldehyde or ketone was to add one of these 3 reagents. Hydroxylamine is, I'm just going to write it, for some reason PowerPoint ate the structure. So you would have an oxime, or so you would take hydroxylamine, which, let me rewrite this. So this is an N with an OH. So the hydroxylamine is nothing more than a primary amine. So when it reacted with your ketone or your aldehyde, it would form a double bond, and then this would actually precipitate from solution. So if you thought you had an aldehyde or a ketone, you would add a hydroxylamine to it. If you saw it precipitate, that's a positive test for aldehyde and ketone. Doesn't react with esters, amides, carboxylic acids, doesn't react with those. Or you could use what's called a 2,4-dinitrophenylhydrazine. The hydrazine is NH2NH. That's a substituted version of N2H4, which was our, which reagent was that? Oh, that's Wolff-Kishner. And then there's an NO2 group over here. The beauty of this is that when it formed a 2,4-dinitrophenylhydrazone, that these were highly colored materials. They would precipitate and they would have a color anywhere from red to orange. The oximes were usually, I believe, they're just colorless. Or you could use a semicarbazide, which had an NH2, NH, and then another NH2 on the other side. Semicarbazides also precipitated from solution without spectacular colors. So what we would do is, if you did any or all 3 of these tests, it would tell you whether you had an aldehyde or a ketone. Now, you'd always have the melting point or the boiling point of the liquid. So then you would go to these books that had all possible aldehydes and ketones listed according to boiling point or melting point. And then they would have the authentic material, and then they would have the melting points of their oximes, of their 2,4-dinitrophenylhydrazones, or their semicarbazones. So if you did all 3 of these, there would be one aldehyde or ketone that had the melting point of all 3 compounds match up. And then you would say, that's the one I have. Of course, when you made these solids, you then had to recrystallize them and purify them to get the right melting point. That was just for aldehydes and ketones. So, needless to say that, and none of these tests really work all that well. I think 4 was kind of too much, but that's what they gave us. So that's what we had to do. And 4 hours a week wasn't enough. So you'd go get the secretary to give you the key, let you in the lab, and then anytime you had free time, you would go in there. It was sort of an introduction to research, except nothing really worked that well. And I was reading through the books on these procedures, not necessarily understanding what was going on. But that was my undergraduate experience. And I teach this nowadays, so I guess there must have been something in there positive. But that's how we had to determine the structures of the molecules in the old days before spectroscopy. So, I mean, Markovnikov, Zaitsev, how they got their structures, you know, was difficult. You might get 2 or 3 in a lifetime. But nowadays with spectroscopy, we can get them in an hour, if we're good. So that's where these were historically used as what we call derivatives. So to relate that back to lab, what you're doing this week, or what you have done, is that you have the boiling point of an unknown ester, and you basically replace the carboxylic acid part with a 3,5-dinitrobenzoic acid part, and you know what the melting, you'll have on the table the list of potential esters, and then what their 3,5-dinitro derivatives would be, and that would help you narrow down the list. Of course, our ultimate test is the NMR. That tells us exactly what we have. So that's one use of these oximes and hydrazones and semicarbazides. That's how we use them. So that's a little bit of a sidelight there. What happens if I use a secondary amine? Well, if I use a secondary amine, now with only one nitrogen, I have a problem. And my problem is that I only have one hydrogen that's going to end up being transferred. I don't have a second hydrogen to eliminate from the nitrogen. So this is going to have a slightly different second mechanism, part of the mechanism. So nitrogen still comes in and adds to the carbonyl. I'm still going to form the zwitterion, and I'm still going to have the O- come down and grab the only hydrogen left on that nitrogen. This is still going to be done with heat, although it doesn't necessarily have to be done with heat. And so right now, I've done the addition part, but I need to redraw the molecule to do elimination. And just so you know, this thing right here is called a something like a hemiaminal. Although I don't think it's an aminal, I think it's like an aminone. Although I've never seen that term before, because it's ketone or aldehyde. So they never tell you like if it's a hemiketal or hemiacetal. This is a hemiaminal because it's half of an enamine. I didn't know what it was either until we accidentally made one day. We were trying to make a shift base. Well, a student and a former colleague were trying to make the shift base. And so after they basically took every round bottom I had and made some brown tarry stuff in it, and so the lab was like filled with nothing but brown tarry stuff and not the right compound, I said, well, let's try this. And then we made some beautiful yellow crystals, sent them off. They got the structure sort of determined by X-ray, and it came back and it's like, oh, it's that. What do we call that? And then I had to look it up. Hemiaminal. And then we had to try and do something else, but that's a tale for another time. So I'm going to rewrite the molecule like this. So when we're doing our elimination using a secondary amine, the elimination is going to come from the carbon that's attached to what was the carbonyl group. So now I'm going to lose this hydrogen and the hydroxide. So I'm still going to eliminate water, but now I'm going to end up forming a carbon-carbon double bond. So the final product's going to look like that. And I'll rewrite it over here. No nitrogen. Anybody know what you call that? No.
I'm confused about what's going on there. So the electron in the bottom of the first structure, when the hydrogen, the electron from the hydrogen goes in, so then it causes the OH thing?
And then the OH and the hydrogen recombine to form water. Okay. This is the same ugly mechanism as it was before, right? Because we've got to assume that somehow that hydrogen gets on that OH, and that's why I think there might be two of these molecules reacting together. This is called an enamine. Which is the title of the slide. But what's this? And what? Oximes were on the previous page. Why is it an enamine? Why is this an enamine? What? Yeah, so that's which part of the name? Ene. What's the other part? The amine. So it's half alkene, half amine. So what's this one? Why don't we like those? Right. But we've seen them before, right? They're not stable. These enols are not stable, and they do tautomerize to give you a ketone. So where did we first see these? Triple bond reactions, week 1. So this is an enamine. If I deprotonate this enol, I get what's called an enolate. And so we'll talk about enamines along with enolates later on because they have similar reactions. Okay, so different mechanism for a secondary amine versus a primary amine. Let me kind of skip ahead here to an empty slide. If I did this reaction, I would end up with my N with my two R groups here. And now I'm going to have a double bond that I would place either between this carbon, the carbonyl, what was the carbonyl carbon, get double bond between carbon A or between the carbonyl carbon and B. Where do you think the double bond's going to go? A? Why? It's more substituted, more stable. Are we under thermodynamic conditions? Yes, because we're heating this. We're usually refluxing this. So actually, we would always form the more stable of the enamines. And if we do have a way to make the more unstable one, or the less stable one, we're not going to talk about that right at the moment. Okay, so these kinds of compounds they do actually have a use if you try and react them together. And some of the uses of shift bases are to make molecules that are ligands for metals, because if you use aromatic nitrogen compounds, they can tend to be really flat, and they can come in and grab the metal. So that same project where they filled my lab with black tarry residue or brown tarry residue, ultimately we did get it to lose water, but we actually had to put the metal in place. So the metal helped pull everything together and then form the shift base. We ended up with these beautiful green crystals that we didn't know what the structure was. We sent it out. They did an X-ray diffraction on it, sent it back to us, and I'm like, oh, we just made what we wanted, except now it's bound to a copper atom or copper ion, and we're never getting the copper out. So we could never make the ligand, and it's intact in order to add the copper, but the copper helped put it all together. And then I found out later that there were some researchers in China that were using it as a way to nick DNA. And they made it similar to us, but not quite similar. So sadly, I haven't published that. And I have to find a way to say, but we made a slightly different one, so you should publish it, even though they published it years ago. Still working on that one. But that's what the metal complexes can be used as catalysts. They can be used to do sort of biochemistry things. And so that's one big use of shift bases, is to make them. So the difficult part is to get the water to eliminate. And if the metal puts the structure together, the water just flies off and forms. Okay, so that's enamines, and that's shift bases. Okay, we sort of at the end here have a hodgepodge of aldehyde and ketone reactions. So if you're kind of like, well, these don't really flow together, they don't. So here's the next one, the Wittig reaction. In German, W is a V. So George Wittig won the Nobel Prize for this reaction. Nearly everybody, probably like pre-1930s, that came up with a reaction to form a carbon-carbon bond, won the Nobel Prize. And so his is no different. We're going to take a carbonyl, we're going to react it with this thing called an ylide, which I'll talk about in a moment, and we're going to couple the ylide part with the alkene, or with the carbonyl part of the aldehyde or ketone, to form a double bond and an alkene. So when we talked about sort of Heck and Suzuki couplings, the idea was that you could make this part of the molecule, you could make this part of the molecule, and couple them together. And so that's what Wittig's reaction allows you to do as well. Where does this part come from? Ketone. Where does this part come from? Ultimately, that part comes from an alkyl halide. So what we do with this alkyl halide, with the A and the B part, is we react it with triphenylphosphine. So 3 benzene rings on a phosphorus. Triphenylphosphine we have only seen once before. That was in Heck coupling. Okay. So what it's going to do is, phosphorus being below nitrogen on the periodic table is a stronger nucleophile. It's going to come in and it's going to kick the bromine off. So that this is a CH. So that what it does is the phosphorus comes in, kicks the bromine off, that leaves a negative charge, or sorry, that leaves that neutral. The bromine ion is a counter ion, and it'll just kind of hang around to counter the phosphorus. So the idea here is I just did an SN2 reaction where the phosphorus is now attached to the carbon. Then what I'd like to do is then I would like to take butyl lithium. So butyl lithium is four carbons with a negative. So this is the lithium equivalent of a Grignard. Much easier to work with. In particular, butyl lithium is used as a catalyst to, well, it's used as an initiator to make rubber for tires. It's used to deprotonate stuff. There's probably tanker car quantities of it floating around the U.S. right now. You can buy it in large bottles. It's not too bad. It doesn't catch on. You got to work to get it to catch on fire. There are other ones, though, that will instantly go with organolithiums. This one's not too bad. So for butyl lithium, the negative charge, this is just going to simply deprotonate that hydrogen. And so when it does that, we make a C- with the phosphorus plus the bromine's gone. And so what I've done is I've now made a zwitterion with the phosphorus and the C-. And that is what's called an ylide. So the thing to ultimately remember here is it's the alkyl halide that I'm using to make that ylide. And that ylide is now going to react with the ketone or the aldehyde. So how does that happen? And this is not a mechanism I would ask you to reproduce, but I'm just kind of showing it to you. So what we have is we have the ylide reacting with the carbonyl. The negative charge on the carbon is going to be used to make a carbon-carbon bond. The oxygen, the pair of electrons on the oxygen is then going to react with the phosphorus. So that arrow isn't quite correct. It goes from the double bond. And what I end up doing is forming a square. With the carbon-carbon bond formed, it's carbon phosphorus, PO, and CO. So this is called an oxaphosphatane, or it's also called a betaine. And so what happens is this isn't very stable, or it's not as stable as actually forming a double bond between the phosphorus and the oxygen. So the pair of electrons moves this way. We now form the double bond between the carbon of the carbonyl and what was the carbon of the alkyl halide. And then you also end up making triphenylphosphine oxide, which is precipitates from solution and is a mess to get rid of. But it's the natural product of this Villiger. So again, if you think about real syntheses, I may be making this compound that's got 40 carbon atoms in it, and there's a strategic double bond that I'd like to make. So what I might think about is saying, okay, the left half of the molecule, some team's going to work on synthesizing. The right half, some other team's going to work on synthesizing. And when the one team gets the ketone or aldehyde and the other team gets the alkyl halide, we'll go ahead and use a Villiger to couple those two big groups together. The same way you would with Heck coupling or Suzuki coupling or even Gilman, the Gilman reagent. So that's the importance of Villiger, the Villiger reaction. And again, he not only formed a double bond, or not only formed a carbon-carbon bond, he formed a double bond. So that's Villiger. How would I show you a Villiger reaction? Let's say I did something like this. Ketone plus alkyl halide. Step 1, triphenylphosphorus. Step 2, butyl lithium. Step 3. There is no step 3. So those would be the 2 steps. These 2 steps turn this into an ylide, and so the final product would have a double bond, and then my alkyl halide. So that's how I would ask you to do a Wittig reaction. Okay, so that's an important reaction of an aldehyde or ketone.
So, for instance, if we were given a cyclohexane that has a methyl group next to the ketone on one side, is that going to determine which side
whether you're going to get like an E or a Z or a...
Yeah.
Yes. It would, but we're not going to go into that level of depth. So remember, so the thing I should point out at this point is all these reactions we're learning them like at the surface level here. If you want to do regio or stereo selective reactions, somebody has come up with that, but we're not going to do that deep dive. Okay? So yes, you could probably actually make it in both forms, but we're not going to we're not going to learn how to tweak the reagents and make that happen. Or which one, unless one is clearly favored. And in this case, they may play a role. It depends on the conditions. So in this case, I'm not going to actually make you have that choice. Exactly. So the problems I'm going to give you probably doesn't matter. So there's an example of a Wittig reaction. All right, the next hodgepodge of alkene reactions is Baeyer-Villiger oxidation. So in this case, what happens is that I'm going to react a ketone with a peroxy acid. Okay, so this is an OOH. So the peroxy acid. If I had time to listen to notebook pages flip for 5 to 10 minutes, I could ask you and say, where have we seen a peroxy acid before? Anybody got that at the top of their head? What? No. No.
Free radical.
No. It's actually last semester.
Oxides.
To make what kind? Epoxides. So we can use the peroxy acid to make epoxides. And what happens in that is one of the oxygens in the peroxy acid plops down on the double bond, and you make an epoxide. So the same thing is going to happen here. One of these oxygens is going to come over, and it's going to insert itself between the carbon and the R group. So that now I'm going to make an ester. So you might say, what would you use that for? And one thing that we do have a Regio Selectivity here. The oxygen atom will end up inserting on the side which has the larger group attached. And that's because of the mechanism which we're not going to get into. So there is a Regio Selectivity here in terms of which side of the carbonyl we add to. So in terms of Baeyer-Villiger oxidation, where does this become important? And quite honestly, it's not really necessarily that important with straight-chained ketones turning them into esters. It'll work, but it doesn't save us a whole lot of time. Where it does save us an incredible amount of time is, let's say that somebody said, I want you to make that cyclic ester. That cyclic ester is called a lactone. And so there are lactones that people make as drugs, as natural products. So how would you make the lactone? Well, what you'd almost have to think of here is if this was from a straight chained or an open chained molecule, you've got to somehow get the chain to close, which on paper looks good. But remember, we've got a bazillion other molecules in there. So once you do something to one side, it may react with the carbonyl of another molecule and not close on itself. The beauty here is that if I want to make a lactone using a Baeyer-Villiger, first of all, I cut my ring down by 1. Because if I'm starting with a 5-membered ring, I'm going to add an oxygen to make a 6-membered ring. So that this is a real straightforward way of converting cyclopentanone into that 6-membered lactone. So where this reaction becomes really important is when you want to make cyclic esters. And the same rules apply. If I had a methyl group on one of these sides, the methyl group would end up down here because that's where the oxygen would insert itself. Okay. So that's where Baeyer-Villiger oxidation really comes into play. Or maybe you have some super complicated ester that you can make the ketone version of, and then you just plop the oxygen in and make the ester. All right, so there's Baeyer-Villiger oxidation. Next. So there are 2 qualitative tests for aldehydes. When I started, I said with amines and hydrazones and things, those were tests that we used to determine if your molecule was a ketone or aldehyde versus everything else. So what happens when that molecule precipitates out and you go, I have a ketone or I have an aldehyde? It turns out that there's 2 qualitative tests that will oxidize an aldehyde only. And these 2 reactions then could be used to oxidize an aldehyde if you had like a primary alcohol in your molecule, because these only react with aldehydes. So one is called the tolerance test. So in the tolerance test, what we do is we take an aldehyde and we react it with silver plus metal that's made up in ammonia and hydroxide. And this reagent you have to make up fresh because if you store it, it tends to become explosive after a while. So, well, again, pick the bottle up with the hand you don't write with, if you're going to do that. But it tends to form silver azides, and those are bad. So we make it fresh if we're going to use it. Or you can actually buy it, because I'll put in the folder a link to some YouTube video that I find, which I know is out there. So I'm going to oxidize the aldehyde to a carboxylic acid, except the problem is carboxylic acid is in basic conditions, so it's a carboxylate. The really good part of this is the silver plus becomes a silver metal. So in this reaction, what happens is if you put an aldehyde, and you could put, for instance, a sugar molecule that has an aldehyde in its open chain form, you throw that in with this tolerance reagent and you swirl it around in the round bottom flask. The silver metal is formed and it adheres to the inside of the silver flask, so that basically you can make a round bottom with silver on the inside so it looks like a Christmas ornament. This is the old way to make mirrors. And so the older way, if you wanted to make a mirror, was to put this reagent on a piece of glass. It would coat the glass in silver, and you made your mirror. Which is why, and I don't remember which. So when you shoot a silver bullet, who do you kill?
Vampires.
Vampires or werewolves? Not vampires? No, that vampires is steak, right?
Yeah.
But yet who can't see their mirror vampires? So somehow this example doesn't quite work. If it was a cross between a well, I don't know. I don't know if werewolves can see themselves in mirrors, but if they have this aversion to silver, they couldn't see their reflections in a old silver mirror because it's really made of silver. I thought that was a reason for vampires not being able to see themselves. But how about a silver tipped wooden stake? Anyway, this is how we can coat glass in silver. We've done this in the past with the little kids. They make like little Erlenmeyer flasks that are silvered and take them home, and there's safe versions of this reagent. But that's the tolerance test. So if I had a molecule that had an aldehyde and a secondary alcohol, and I wanted to oxidize one versus the other, tolerance would touch the aldehyde. It would oxidize. It wouldn't touch the secondary alcohol. The other reaction that you may have actually done in biology or in a biology class is what's called Benedict's test. So in the Benedict's test, what you do is you take an aldehyde, typically of what's called a reducing sugar, and you react it with copper 2, basically in a hydroxide solution. So copper 2 from general chemistry is what color? It's dark blue. And so what happens is that, again, you're going to oxidize the organic part to a carboxylic acid, but it's in basic condition, so it gets deprotonated. The copper now gets reduced from copper 2 to copper 1. That then forms a copper oxide, copper 1 oxide. This copper oxide is brick red in color, and it's brick red because that's the pigment they use to make bricks out of. So that's the name. So if you've ever done that, now again, I'll put videos to both of these. I have the links in previous presentation or previous videos. So what you would do is if you take an open-chained form of a sugar, we talked about this earlier in the week. If you have an open-chained form of a sugar, and it doesn't take very much. So when we talked, for instance, about glucose, we said 99% of it is cyclized, and less than 1% of it is open. But that less than 1% part will easily react with the copper, so that you start out with a blue solution, you heat it with a Bunsen burner, and eventually it turns red, and then it also then precipitates out the copper oxide. And I think there's different versions of this that will give you different colors depending upon the sugar that you start with. Because I have seen people end up with like green or yellow, which would be, I haven't done them, it would be helpful in the future for me, but sometimes nobody's asked me for what kind of sugar is in some sort of rogue piece of bread yet, but if they did, that's how I would do it to figure out what it is. So both of these were qualitative tests to determine an aldehyde from a ketone, but in the case of the Benedict's test, you use that as a test for a reducing sugar, and the reducing sugar is one that has some open chain form as an aldehyde. Sucrose would not work with this because the 5 and 6 membered rings are pinned together and they don't break apart. Okay. Reductions of aldehydes and ketones. We already know how to do that, right? What do I use? Well, lithium aluminum hydride is overkill, but it would work. Sodium borohydride would work. Both of those. The other reagent that might work would be H2 and rainy nickel. H2 and platinum palladium? No. So we've talked about that before. I'm not going to go back over this. So what we did was we kind of cut the aldehyde and ketone chapter in half. You might say, what about the first part of the chapter, which was a review of how to make aldehydes and ketones? And what I will probably do is to come up with a take-home quiz, or I might even have one in Canvas that you just go on as a multiple choice test. You got to learn this stuff. Well, we'll see what I got. Paper's better, but computer is a better grader, because then it's not me grading. So either way, all those reactions in the first half of the chapter, those are all review. So I know everybody would review those on their own, and I'm just going to give you something to check yourself with. On Monday, I'll have a homework or whatever problem set for you to be able to use. All right, if you got questions, email me. Monday, your homework quiz problems are due that were in Wednesday's folder.